The concept here is that now you have the gradient, which in reality is not only applied to this column, but also encompasses everything from the frequency encoding, which includes not just your entire section from bottom to top, but also all the voxels. So essentially, you have all the voxels that rotate during the recording process. And as you record them, they send you signals with different frequencies and different phases, which are crucial for the process. This allows you to perform differentiation and determine precisely where they are coming from any location and with what intensity. The intensity, in turn, depends on the level of magnetization. This gradient is a crucial component in the imaging process as it helps in mapping the spatial location of the signals. The frequency encoding is a sophisticated technique that captures the entire section, ensuring that no detail is missed. Each voxel, which is a tiny unit of volume, plays a significant role in this process. As they rotate, they emit signals that vary in frequency and phase, providing essential data for analysis. This differentiation process is vital for accurately determining the origin and intensity of the signals, which is influenced by the magnetization level. Based on magnetization, the frequency or location and phase depend on the y-axis gradient and the x-axis gradient. You will know how this point rotates. They rotate at different speeds, and 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 they rotate at different speeds. Right. In the y-axis, it rotates towards you in an earlier time. And since it comes to you in an earlier time, you now know exactly the result of the gradient you applied regarding the location of the voxel. Each voxel rotates in the x and y, leaving different frequencies. What does the frequency depend on? It depends on what you applied, and the phase encoding in the y comes to you at a different time, one earlier than the other. What is it based on? On the gradient in the y-axis, we place it on lines in Arabic, starting with what? This is the 90-degree pulse, and this is the 180-degree pulse. So, what do you start doing next? Hadi. With 90-degree slice selection and some 180-degree slice selection, when you give 180, you need to have a slice selection gradient to differentiate between the slices. Here, you will apply the phase encoding gradient. Okay, now record the frequency encoding gradient. So why do I keep the phase encoding on all the time while I turn the frequency encoding gradient on and off? The answer is that if you apply frequency encoding with phase encoding, the two gradients will work in opposite directions. What will happen, doctor? They will cancel each other out. So you can't do a continuous application of both. You only apply it during the signal acquisition and then turn it back off. So it confirms that it works with revising and devising, and you detect your signal in the middle. What is this phase encoding? These are degrees or steps, and for each step, you repeat it again with a new step and a new angle. The team that is placed at the reception because you want to determine the location of the voxel, how will you define it? Now, you will apply the gradient in the y-axis and the gradient in the x-axis. I applied the gradient in the x during the receiving phase because I want them to come to me at different frequencies. So when you receive them at different frequencies, you can simply project and say what? These are the applications at a certain speed. Do you know where they are coming from? They are coming from this column. So What about the one that came to you with a lower speed from this column? And what about the one lower than this column? The one lower because your English is for you to apply it, right? So do you know where each point is? Is that clear? Okay. So if you want to differentiate in this column itself, what do? What you applied? Why? This will come to you at a different time than this, different from this, different from this, different from this. The idea is just that I'm saying, why is the frequency not placed in the syntax? I mean, it's placed at the receiver. The two are not placed one under the other on the lines that you have drawn horizontally. So, do you want to do it before you stop? It means in the middle, how between 90 and 180, like the phase should not be at the receiver. This is the confusion, meaning this is 90 and this is 180, and this is the phase, and this is the phase. Do you want to put it here? 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 Yes. Why don't you put it here? Why don't you put it here? Because he puts it when using the signals that I want to understand. Nice. I understand that they use it a lot to determine the exact location of each pixel and each voxel. Do you want this to be continuous, or is it activated? And it should be exactly that. So do you want it to be this way or not? Or should it be done and removed? To place each point beautifully, you want to stabilize it correctly, right? Yes, great. I want you to imagine something specific with me. I give the image A, I apply a gradient, and I apply both gradients together. And both work together at the same moment and are continuous. What will happen? This is not used in reality. This is what Harak says is not used in reality. The method that Harak talks about is not actually used. It will create a point in the signal that will be captured from your design. So what is the solution for them to overcome this issue? It was said that you will use it during the design of the signal. I will take a video for you that explains this topic at the voxel level and the image level. Why? If we apply the idea I told you about, it won't work exactly. What will happen specifically? Okay. The case-based filling has become a stage in the case-based filling process. Each point in the case base contains information from the entire image. Each point in the case base is filled, and as you take each step in phase encoding, it fills a line in the case base. Each line in a step begins to fill a line in the case base, and so on. Therefore, the number of lines determines your scan time or the number of phase encoding steps you take. It starts to divide the frequencies. You take the two signals we mentioned, which are high frequency and low frequency, as I explained to the doctors last time. I understand this, but why does it take data from phase encoding every time? They increase the degree, so each time they perform differentiation on the phase of the proton differently, expanding the individual. But isn't frequency the same? No. Your frequency is constant, the same magnitude every time. I remember that the frequency also differs. No, it's the phase that differs. That's why it's called phase encoding steps. Each time it is supplied with magnitude. So when I was updating the drawing, I was changing the phase, not the frequency. The frequency and even the frequency encoding gradient do not change even without the case-based topic, right? No, it does not change. Each voxel in X will spin around at a different speed in the 3D space. When you create edges along the x-axis with the initial step, it will cause each voxel present to spin around in a unique manner at a different speed. This unique behavior is what distinguishes it in relation to the initial step. The second line will do the same differentiation. The idea is that the signal coming to you can be decoded by its name, sync pulse. This sync pulse is what you are receiving. So how will you decode it? You will decode it using Fourier transformation, which converts it into different frequencies. How does it do this? Through mathematical equations that we won't delve into. But the idea is that it takes the large pulse, or the incoming one, that contains all the information. The first time, it fills the first line of the K-space. The second time, it fills the second line of the K-space. The third time, it fills the third line of the K-space, until the entire K-space is filled. Are you okay, Jistra?